In this presentation, we discuss connecting a resistor and a capacitor to an AC voltage supply, and we think about what happens when we connect them in series and also in parallel. So we recall that impedance is a way that we can measure how much these different components resist the flow of electricity in a circuit, an AC circuit. And so we now have three different forms of impedance. We have resistive impedance, and we can write that as just the resistance, and then it has an angle of 0. We could, and that angle of 0 is because, of course, the current through the resistor and the voltage across the resistor are in phase with one another. We can write the impedance for an inductor as the inductive reactance with an angle of 90 degrees. The angle of 90 degrees tells us that when you're looking at an inductor, the voltage across the inductor leads the current by 90 degrees. And now we also have defined the impedance for a capacitor, and that's the capacitive reactance with an angle of negative 90. And that angle of negative 90 just tells us that for a capacitor, the voltage across the capacitor lags the current by 90 degrees. So let's look specifically if we only had a resistor and a capacitor in our circuit and what our impedance diagram would look like. So we would have some impedance for the resistor, and that could be drawn, of course, on the real axis, and that impedance is just going to be the resistance component. If I also had some capacitive impedance, then I would draw that in the negative imaginary part of our impedance diagram. And so when I combine these two impedance values together, I get the overall impedance in my circuit. And of course, the overall impedance is going to have some angle associated with it. If I have a resistor and a capacitor, and only a resistor and a capacitor, that impedance angle is going to be negative. And depending on that angle, that will tell us how much of the impedance is resistive. So the resistive piece is the magnitude of the impedance times cosine of the angle, and then our reactive piece, this is our capacitive reactance, would be the total impedance value times sine of the angle. So as the angle gets smaller, then the impedance is more resistive impedance. As the angle gets larger, the impedance is more, in this case, capacitive impedance. So if I know what the resistance is and I know the capacitive reactance or the reactance in general, I can figure out the overall impedance by just using the fact that I have a right triangle, r squared plus the impedance squared, well, the reactance squared, square root, and I can always find the angle, as we've done previously, for an inductor by taking the reactance piece and dividing by the resistance and taking the inverse tangent. And so now these plus minuses here are going to make sense because our angle will always be negative if I have more capacitive reactance in my circuit than impedance reactance, and it'll be positive if the inductor reactance is basically dominating over the capacitive reactance. So let's look at a couple of examples. We now know how to write down the impedance for a resistor and a capacitor from previous lectures. So let's apply it to situations that are in series and parallel. So just as a quick reminder, the equivalent of Ohm's law for AC is still valid. So instead of V equals IR, we have V equals IZ, where Z is our impedance. All of these components are in phasor notation, so they would have magnitudes and angles associated with them. And we have to treat them like phasors, so I would have to add, subtract, multiply, divide in terms of this complex notation. I know that when components are connected in series, Kirchhoff's voltage law still has to be satisfied, and the end result is that I can take a combination of components that are in series and I can write them as some total overall impedance by just adding the values together. That gives me the total impedance. I also have, similar to Ohm's law for resistors, I have the voltage divider rule for impedance values that are connected in series. And so the voltage across any one of these impedance components is just the value of that impedance component over the total impedance times the total voltage across those components that were connected in series. And we're going to start to use some of these expressions. Again, these are all in phasor notation, so I have to make sure that, that I treat them as phasors. In parallel, I know that Kirchhoff's current law has to be satisfied so that the current entering has to equal the current that's exiting, and the end result from that was that the impedance values add as the reciprocal. So I can take a number of components which are connected in parallel, and I can replace them with some equivalent impedance, where that equivalent impedance just adds as the reciprocal. I know that when I have current entering the junction here, that it will split between these impedance values, and so I can use the current divider rule for parallel situations, similar to resistors connected in parallel. So the current through any particular impedance component is equal to the total equivalent impedance, which is the total impedance from adding these as the reciprocal, divided by the impedance of the value that I'm interested in knowing what the current is through that component. So this might be I1 and Z1 times the total current that's entering the junction where the components are connected in parallel. So again, phasor notation must treat these in terms of phasors, add, subtract, divide, multiply in that way. So let's look at an example where I have a resistor and a capacitor that are connected to an AC source. So I have an AC source that has a maximum amplitude of 25 volts. It's sine omega, so my angular frequency is 1,000, and I have a phase angle of -10 degrees. My capacitor is 2 microfarads, and my resistor value is 1 kiloohms. So I want to determine the total equivalent impedance for these two connected in series. I want to know what the total current is, and then the voltage across each one of these components, and then I'm going to sketch these in phasor notation so that I can find the phase difference between the voltage supply and the current, and then the resistor and the capacitor. So the first thing that I would do is I would realize that these are connected in series. So the total impedance of these two components together can be replaced by one equivalent impedance value. So I could take these two and replace them with a single box here, which I have not done in my picture, which has some total equivalent impedance. So I need to be able to write down what the impedance is for each one of these components. The resistor has an impedance value of 1 kiloohm with a phase angle or an angle of 0. So that's just 1 kiloohm in terms of complex numbers. I can determine what the impedance value is for the capacitor. It is just the capacitive reactance with an angle of -90. I need to determine what the capacitive reactance is, and I know that the capacitive reactance depends on what the angular frequency is and the capacitance. So this is supposed to be a C here, not an L. That's a copy and paste error. So this is the capacitive reactance is 1 over the angular frequency times the capacitance. So this is 1 over 1,000 multiplied by 2 microfarads. I need to make sure I have all my units correct, so I'm going to convert microfarads to farads. So that's 2 times 10 to the minus 6. When I multiply that by 1,000 and then I divide, I end up getting 500 ohms. In order to be consistent and use the same units, since my resistor value was in kiloohms, I'm going to go ahead and I'm going to use kiloohms here, so 500 ohms is equivalent to 0.5 kiloohms. So I could write down that the impedance for the capacitor is 0.5 kiloohms with an angle of -90, and if I write that in rectangular form, this is just has an imaginary part that's negative of 0.5 kiloohms. So the total equivalent impedance for these connected in series is just a matter of adding the resistive piece to the capacitive piece, and when I add them together, I get 1 kiloohm minus J 0.5 kiloohms. But of course, we probably don't want it in rectangular form. We want to convert that into polar form. And so I can take that complex number and I can convert it into polar form by taking the square root of 1 squared plus a negative 0.5 squared, and I get 1.12. And I can figure out what this angle is by taking the inverse tangent of negative 0.5 over 1, and I get a negative 26.6. So this resistor here and this capacitor are equivalent to a single total impedance that has a value of 1.12 kiloohms and an angle of minus 26.6 degrees. So once I know what the total impedance is, I can use Ohm's law and I can figure out what the total current is in the circuit. And then, I can use the equivalent of Ohm's law for AC. And then I can also go back and I can figure out what the voltage is across each of the components. Before I do that, I need to write down my sinusoidal varying voltage supply in phasor notation. And so writing this in phasor notation, I would take the amplitude and I would divide by the square root of 2 to put it in terms of the RMS value or the effective value. And this phase shift is negative 10 degrees. So 25 over the square root of 2 is 17.7, and then the phase shift is negative 10 degrees. I can now use the equivalent of Ohm's law for AC, and so the total current is just the voltage over the total impedance. And so this is 17.7 with a phase shift of negative 10 divided by the impedance of 1.12 with an angle of minus 26.6. And I find that the current is 17.7 over 1.12 kiloohms is 15.8 milliamps. And then minus 10 degrees, I'm dividing, so minus 10 degrees minus a minus 26.6 degrees is 16.6 degrees. So my voltage supply and my current that's coming out of that voltage supply are not in phase with one another, and I wouldn't expect them to be because I have some capacitance in that circuit. If I wanted to determine the voltage across the resistor alone, I could use the equivalent of Ohm's law for AC, and I would take the current that goes through that resistor times the impedance of the resistor. And so the current is 15.8 milliamps with a phase shift of 16.6. The current is, that's the current. The impedance for the resistor is 1 kiloohm, so this gives me 15.8 volts with a shift of 16.6 degrees. In the same regard, I can find the voltage across the capacitor. It would be the current through the capacitor times the impedance of the capacitor. These are in series, so they both have the same current flowing through them, 15.8 milliamps. And then in the terms of the capacitor, the impedance is 0.5 kiloohms with an angle of negative 90. So if I take 15.8 and I multiply by 0.5, I get 7.9 volts. And if I multiply these two complex numbers, that means I add these angles together. So 16.6 plus a negative 90 is a negative 73.4. So I now have the current that's coming out of the source and going through both of these components, and I know the voltage across both of these components. If I wanted to, I could also check Kirchhoff's voltage law and make sure that it's valid. So if I add the two voltages, the voltage across the resistor and the voltage across the capacitor, they should add up to the voltage of the source. Now, of course, with Ohm's law, this was very easy with just resistors because I could look at these numbers, add them together, and they had to equal the source. But I can't just look at these numbers and see that it works out. I would have to add these in phasor notation and then convert them back into polar. I'd have to add these two values together using phasor notation, which means I would have to put them in rectangular form, add them, and put them back into polar form to make sure that I get the source here. So Kirchhoff's voltage law is still valid, but I don't expect that the numbers out front are going to equal, the number out front here. I can make a plot now of these different values. So the voltage supply is at an angle of negative 10 degrees. The current is at an angle of 16.6. The voltage across the resistor is also at an angle of 16.6. This makes sense because the voltage across the resistor and the current through the resistor are always going to be in phase with one another. On the other hand, when I go ahead and I put in the voltage across the capacitor, the voltage across the capacitor is at negative 73.4, and it's at a 90-degree shift with the current. So the current that's going through the capacitor leads the voltage across the capacitor by 90 degrees. But if I add the voltage across the capacitor and the voltage across the resistor, I should get the source. And if you think about this in terms of vectors and using the parallelogram method, I've tried to draw these so that it looks like they would add together. Part of the question was to ask how do the voltage of the source and the current that's coming out of the source, how are they related to one another in terms of their shift? And so we see from this picture that the current is actually leading the voltage, right? It reaches its maximum first before the voltage supply does. And the angle between them is 16.6 minus a negative 10, which is 26.6. So the current leads the voltage by 26.6. This number should make sense because if I look at my total impedance in the circuit, the angle was 26.6 and it was negative. The negative sign here for the impedance, remember, implies that the voltage lags behind the current by 26.6. So the minus sign there is lags for the voltage. And what we're saying here is that the current leads by 26.6. So the same thing, right? So if I could say that the voltage lags by 26.6 or the current leads by 26.6. So, the other things we notice, of course, is that the voltage across the resistor and the voltage across the inductor they are out of phase with one another by 90 degrees as well, which is what we would expect. All right, let's consider a capacitor and a resistor connected in parallel. Basically, we want to find the total equivalent impedance, the total current that's coming out of the source, and in this case, the current is flowing through each of these components. And then same sort of question, what is the phase difference between the source voltage and the current that comes out? And then how does the current through the resistor and the capacitor compare? So we know that we can take these two components and we can replace them with one equivalent total impedance. And our goal would be to figure out what that total impedance is so that we can then solve for what the current is that's coming out of the AC source. So in order to do that, we need to write the impedance of each of these components. And so the resistor has an impedance of 300 ohms with an angle of 0, or it has a real part only. The capacitor has an impedance that is the capacitive reactance, and in this case the capacitive reactance is given to us as 200, so 200 ohms with an angle of negative 90. We can write that in rectangular form as a negative 200 complex part only. And now we'd like to take these two components and replace them with one big box here, which is some equivalent impedance. So we know that the impedance value for components in parallel adds as the reciprocal. And if we have only two components, there's a way we can add them that we've done in previous examples when we were talking about inductors, but in this case we're going to go ahead and use the reciprocal form. So I would take 1 over the first component, which is the resistor, and then add to it 1 over the second component, which is the capacitor. So 1, of course, is just a real number, and that's the same thing as 1 with an angle of 0 for both of these at the top. And then I'm putting in the components at the bottom. So in order to figure out what these values are, I'm going to have to use division. So I need to write down what 1 over 300 phase angle of 0 is, and then 1 over 200 top is phase shift of 0, and then minus 90. So if I take 1 over 300, I get 0.00333, and then 0 minus 0, I get 0. If I take 1 over 200, I get 0.005, and if I take 0 minus a minus 90, I get a positive 90. So after I have these in my polar form, I can convert them back into rectangular form. I have a real part, and then I have a positive imaginary part for the second term. Now we're not done yet because this is 1 over the impedance, and I need to figure out what the total impedance is. So I need to convert this back into polar form. So if I take 0.0333 squared plus 0.005 squared, I get 0.006. And if I figure out the angle, which is the tangent inverse of 0.05 over 0.003, I get 56.3. So basically I'm taking this complex number, which is 1 over the impedance that's in rectangular form, and I am converting it into polar form. I still have 1 over the impedance, so if I want to find the total impedance, I have to take the reciprocal, right? I have to flip these, and so the total impedance is 1 over that value. I can write this 1, of course, as 1 with a phase angle of 0, so 1 over 0.0060 is 166.7 ohms. And then reciprocal just means you switch the angle, which we've talked about in previous lectures, or you can imagine that there's a phase angle of 0 up here. So this is, or phase shift of 0, this is negative 56.3. So the two components that I have here can be replaced by one equivalent impedance value of 166.7 with an angle of minus 56.3. All right, so here's my picture. Here's my total impedance, and my goal is to figure out the total current that's coming out of the source and also to figure out the current through each of the components. So the total current that's coming out of the source is just the total voltage of the supply over the total impedance. So my total voltage was 15 with an angle shift of 20 degrees, and then my impedance is 166.4 with an angle of minus 56.3. So if I take 15 and divide by 166.4, I get 0.0901 amps. And if I take 20 and I subtract a negative 56.3, I get 76.3. I can also figure out what the current is through the resistor. Because these components are all connected in parallel, that means that they share the same voltage. So the voltage across the resistor and the voltage across this capacitor are both 15 volts with a phase shift of 20 degrees. So the current is just that voltage over the resistance, the resistive impedance, which is 300. So 15 over 300 is 0.05. I'm missing the amps there. That should be amps. And then 20 minus 0 is 20 degrees. And I can also find the current through the capacitor. Again, they're connected in parallel, so it has the same voltage, and then divide by the capacitive reactance, which is 200 with a phase shift of negative 90. 15 over 200 is 0.075 amps. 20 minus a minus 10 is 110 degrees. Again, we could check Kirchhoff's current law and make sure it's still valid. If we add the two currents, the current through the resistor and the current through the capacitor, they should equal the total current that's coming out of the source. The numbers in front don't add up because, you know, there is this phase angle between them. But if I add them as complex numbers, then the two currents through the resistor and the capacitor should equal the current that comes out of the source. We can make a plot of these. So if we plot the voltage, it's at an angle of 20 degrees. If we plot the current, it's at an angle of 76.3 degrees. If I plot the current through the resistor, it is in phase with the voltage supply across the resistor, right, which we expect. The resistor and the voltage across the resistor are in phase. And if we plot the capacitor current, it is phase shifted from the voltage supply, and the current through the capacitor leads the voltage across the capacitor by 90 degrees, which is what we would expect. If we added the current across the resistor to the current across the capacitor in this phasor notation and thinking of these as vectors, then I should get the total current here, and it does appear that they would add together that way. I also might be interested to know how does the current source compare to the current that's, not the current source, the current that's coming out of the voltage supply compare to the voltage supply itself. And I see that, that the current leads the voltage, and it leads the voltage by a difference in their angles, so 76.3 minus 20, which is 56.3. Again, going back to our total impedance in the circuit is telling us how the current in the circuit and the voltage compare to one another in terms of leading and lagging. So the fact that the total impedance was negative 56.3, that told us that the voltage across the total voltage in the circuit lags behind the current by an angle of 56.3 degrees, or we can say, of course, that the current leads by 56.3. But this value, always, the total impedance, is going to tell you how does the voltage of the supply compare to the current that's coming out of the supply in terms of leading or lagging, and by what angle. We also notice that the current across the resistor and the current across the capacitor are shifted from one another, in this case by 90 degrees, which is also what we would expect.